Okay, so we are chapters 20 and 21 together. A lot of these are review. There might be a few new reactions, so pay particular attention to these. Okay, so the first one, just the basic understanding of nomenclature for carboxylic acids. You drop so ethanoic acid, you're going to drop the E for like ethane, and then you're going to add oic acid. So ethanoic acid is like 2 carbons, and the carboxylic acid will always be this carbon connected to 2 oxygens, and it will always be at the terminal end. So that's ethanoic acid. You do have a lot of, what do you call it, common names, and you can look these up. Malonic acid is the same as this compound here. So this would be propane, drop the E, or I guess keep the E, dioic acid, because there's 2 of them. And that's also malonic acid. You'll need to know this structure because there's a malonic acid synthesis reaction in chapter 22. Magnesium formate. It's good to know that formic acid is just 1 carbon. So this would be formic acid. Formaldehyde then would be 1 carbon with 2 hydrogens. So magnesium formate, whenever the 8 is an ester. So a derivative of the carboxylic acid is the ester. So there's your carboxylic ester, and then the magnesium would be here. So you got the plus minus, and then formate would just mean 1 carbon. So, and the carbon gets 4 bonds, right? So 1, 2, 3, 4. So that's magnesium formate. Dichloroacetic acid. You should know by now that acetic acid, or that ACT, is basically 2 carbons. So acetic acid would put your carboxylic acid component on the terminal end, and then you got dichloro. So this would be dichloroacetic acid. Dichloroacetic acid. And then salicylic acid would be a structure that you would have to look up, and it is part of what aspirin, it's a piece of what aspirin's made out of. So that's salicylic acid. Okay, arrange each group of compounds in order of increasing basicity. And so this means which compounds would likely want a proton. Okay, that's what we're talking about with basic. So if it's increasing basicity, this means it has to be the weakest acid. Because if it's the weakest acid, it's the strongest base. They're kind of opposites, like yin and yang. So the first one, we have just regular acetate, and then you're adding chlorine onto that alpha carbon. Okay, so this is your carboxylic acid, this is your alpha carbon. This is your alpha carbon here, and it has 3 hydrogens. This one has 2 hydrogens and a chlorine, and then this one here, pH is the phenyl group, and that's phenoxide. So one way you could do this is you could actually just protonate that and then compare the pKa's. OH, Cl, CH2, OH, CH3, COH. And you know that the pKa of acetic acid is about 4.74. The chlorine is electron withdrawing group, so that's going to pull the electron density towards itself through an inductive effect. It's a 3 bond, and that's going to make this pKa probably something around 3. So it's going to be less. So this is more acidic. And then this phenoxide is a pKa of a 10. And you need to kind of know that because you will see that on the National ACX exam. So which one is your weakest acid? So your weakest acid would be here. This is your weakest acid. And so your strongest base then would be the phenoxide. Okay, so this is going to be your strongest base. And then the next one, so this would be your strongest base, number 1. And then this would be number 2. And then this would be number 3. This is your strongest acid. This is your strongest acid. Okay, so therefore it's going to be your weakest base. All right, so the next one group, sodium acetylide. So there's sodium acetylide. Sodium amide. So sodium amide would be and then sodium acetate. Okay, so we've already talked about this pKa being about 4.75. This is a pKa of about 23 once you put on the proton. That's an sp carbon. We've talked about that at the very beginning, the first week. And this is an amide. Okay, this is not acidic at all. Okay, amides are not very acidic. So therefore, your most acidic, so your least, your weakest conjugate base, so the most acidic, the least conjugate base would be this one right here, right? CH3CO2Na. That's so that's your most acidic. That's going to be your least, and then you'd have to go to the sodium acetylide, and then the strongest base would be this sodium amide. And we talked about doing the sodium amide, how this is a great base for deprotonating the acetylides. That was a base we used. Okay, now we have the next group, sodium benzoate. So let's do, this is your benzoate. That's benzoic acid, and that is an ester, sodium benzoate. We have sodium ethoxide. Sodium ethoxide, and we have sodium phenoxide. Okay, so let's look at when these are protonated. So when these are protonated, they all have a proton. And this is benzoic acid. This is ethanol. And this is phenol. So we know some pKa's here. This is about pKa of 10. This is a pKa of about 16. And benzoic acid is a pKa of about, I want to say about 5, but let me look for sure, 4. Okay, so the smaller the pKa, the stronger the acid. So this is your strongest acid. And what happens? We're looking these are your conjugate bases. Okay, so this is your strongest acid. And then when it gets deprotonated, that's a conjugate base of that acid. And so you remember the stronger the acid, the weaker the conjugate base. Okay, that was general chemistry. So this is going to be a weaker base. So the stronger the acid, the weaker the base. So your weakest base would be the sodium benzoate. And then it will be your next strongest acid, which is the phenol. So sodium phenoxide. And then your strongest base, which will be your weakest acid, is the sodium ethoxide. Our next group is this group right here, pyridine, sodium ethoxide, and sodium acetate. Okay, so pyridine, already forgotten the other ones, ethoxide, and sodium acetate. So this is ethoxide, and then sodium acetate. That's 2. Okay, so of course if you protonate these, what are you looking at? The pyridinium ion. This would be ethanol, and this would be acetic acid. So you know the pKa of this is about 4.75. The pKa of ethanol is about 16. And then you need to look up the pKa for your pyridine ion. And when we look that up, we see that has, and it's the protonated. This is the protonated. And that pKa is about 5.25. So your strongest base, would be your weakest acid. These are conjugate bases. So the strongest conjugate base comes from your weakest acid. So your weakest acid is pKa of 16. So the ethoxide is your strongest base. And then you're going to have this one, 5.25. So then pyridine. And then your least strong base will be the sodium ethoxide. Okay, the next one we are on is predict the products, if any, of the following acid-base reactions. So we just draw these out: acetic acid plus ammonia. And you have to locate your acidic proton. That's the most important thing there. And then these lone pairs will go and deprotonate. And then you form O minus. And then this is going to be NH4 plus. Now you have to locate where did it go? It went over here. So you're looking at a protonated ammonia. So you might want to get the pKa tables that I gave you. And this is the acetic acid. So you know the pKa of that is about 4.75. And then you're looking at the pKa of the protonated ammonia, which is about 9.26. And so your equilibrium always lies to the weakest acid, which will be your highest pKa value. So you're comparing 4.75 and 9.26. So it goes there. So yes, it does get deprotonated. Phthalic acid, you've seen structure that looks like this. So phthalic acid, remember the potassium PHTH phthalimide, phthalimide. Okay, well, phthalic acid is if this was opened up and it's a diacid. And the other is excess sodium hydroxide. So where are your acidic protons? Right here. And then the sodium ethoxide will deprotonate this, and it will actually do it twice. So you have this sodium carboxylic acid derivative and water. Okay, you're going to get two waters. But so you're looking at the pKa value of water is about 15.7. The pKa here is about 4 because it's carboxylic acid type derivative. So the equilibrium is going to go towards the products because 15.7 is a higher value, which is your weaker acid. Okay, the next one is para-toluic acid. So this is toluene. There's para, so this is toluic acid. And so there's para-toluic acid. Has a pKa of about 10. Really? That would be a pKa of phenol. Huh. Wait a minute. I would guess that's not right. I don't know. I'm going to go on. I don't know why I put a pKa of 10. So look that up and you all can tell me if that's incorrect. My guess it would be more like around 5, but we're just going to go with that. Potassium trifluoroacidic acid. So this is trifluoroacidic acid and this is very acidic. So what happens here is this is going to deprotonate the para-toluic acid, and then you're going to get deprotonation on the product side. O minus, potassium plus, and then Fe carbon OH. All right, now the pKa of this was really low. I have a pKa of 4. I think it's more like a pKa of 2. So it's definitely going to go towards the higher pKa value. And so it's going to go towards the reactants side. Okay, so that's going to go towards the reactant side. Trifluoroacetic acid is called TFA acid. TFA, trifluoroacetic acid. It is a very strong acid. Okay, and it's a very strong acid because of these. Fluorine is your most electronegative element, and it pulls out electron density so far away from that oxygen, makes that very acidic. Okay, our next one is benzoic acid. Benzoic acid and sodium phenoxide. So there's your sodium phenoxide, and so the reaction would be such as this, where you would deprotonate your benzoic acid, and then that would make sodium benzoate and phenol. And so you know to compare the pKa's, you have to find your acidic proton on both sides. The pKa is 10 on the product side. The pKa here is about 5. So it's going to, or 4. it's going to go to the higher pK value. Once again, it goes towards the products. Okay, arrange each group of compounds in order of increasing acidity. Okay, so this is with the proton. So you have phenol, you have ethanol, and you have acetic acid. So you guys know this is a pK of about 5, pK of 16, and pK of about 10. So obviously the more acidic, this is your number 1, the acetic acid, this would be number 2, the phenol, this ethanol would be number 3, the least acidic. Okay, para-toluene acetic acid, that's tosic acid, it's a nice organic acid. Para-toluene, CH3. Ortho, no, next one, acetic acid. So here's your acetic acid. And then you have meta-nitrobenzoic acid. So here's your benzoic acid. And then the meta position is right here, and it's nitro. So this is an electron withdrawing group. So it is pulling the electron density away from this oxygen, which is going to make it more acidic than your normal benzoic acid. The pKa is of the meta is about 3.47, and tosic acid is your most acidic. And I'm not sure what the pK is for that, but let me show you why. When you deprotonate this, make that O minus, and then you have 1, 2, you have several 4, 5, 6 resonance structures. The more resonance structures you have, the more acidic it is. So this is your most, number 1. Number 2 would be this meta nitro, and then number 3, the least acidic, would be this acetic acid. So that's number 3, number 2, and number 1. Okay, the next one we have benzoic acid. Benzoic acid, we have ortho nitro. So there's your ortho nitro, and then the other one's the meta. So we're dealing with electron withdrawing groups and their effect on the acidity of this proton here. So this is electron withdrawing group, electron withdrawing group. This is ortho, this is nitro. So if you look in your reading, there is a page that talks about this. So here your pKa of just benzoic acid is about 4.2. And then ortho is going to have a pK of the nitro is about 2.16. And your meta, pKa about 3.47. So it's actually a factor of 10-fold more acidic if it's ortho. So ortho is more acidic than meta. So pKs, this is most acidic. This is number 2 with the meta. And then number 3 is no substituent at all. Okay, some more common names. Butyric acid. Butyric acid has about 4 carbons. It's called like a fatty acid chain. There's a lot of common names for these. They were around, these fats were around before IUPAC was established. Okay, we have alpha bromobutyric acid. So now we're looking at the alpha carbon here. Okay, and we're going to put a bromo substituent. So we'll decrease that by a hydrogen, and that's your alpha bromo. And then we have beta bromo. So beta bromo would be this one here. So this is your alpha, this is your beta. So then that would be CH3, CH, and a bromine there, CH2, Okay, so bromine group is an electron withdrawing group. So this is going to be your most acidic. Then these two are going to be about the same. Okay, these two are going to be about the same. You're not going to feel much at the beta position, but the alpha position, you would be the most acidic. So, and then these would be about the same. All right, this next problem, what do the following pK values tell you about the electron withdrawing groups of the nitro, cyano, chloro, and hydroxyl groups? So all of these compounds are different substituents on the alpha carbon. So all these have CH2, and then this has a nitro, or this has a nitrile, or the next one has a chlorine on the alpha carbon. And then the last one, oh, the other one has an OH on the alpha carbon, and then the other one is just without. So if you look at the pKa values of each one of these, we have 4.74 for no substituent. And then we put an OH, we have a 3.8, 2.86 for the chlorine, 2.46 for the nitrile, and 1.68 for the nitro. So the more electron withdrawing group on your alpha carbon of your carboxylic acid, so if you increase the electronegativity on your alpha carbon, decrease the pKa value. When you decrease that, so that increases the acidity of this proton. This is the proton that's being affected. So that proton is more acidic if you put an electron negative withdrawing group on the alpha carbon of your carboxylic acid. Okay, going on to the next page of problems. Number 7, predict the products of any of the following reactions. Okay, so we're into the reactions of the carboxylic acid. And, okay, so lithium aluminum hydride, what does that do to carboxylic acid? Well, it is a strong reducing reagent, so it will reduce all the way to the primary alcohol. Keep drawing that as a 6-membered ring. Okay, so we have a 5-membered ring, and then this would be CH2OH. So it goes all the way to the primary alcohol for the carboxylic acid. So the carboxylic acid goes to the primary alcohol using lithium aluminum hydride. All right, the next one, this is an SN2. Nitrile is a great nucleophile. It's a great nucleophile. And you have an allylic bromide. So remember, allylic bromides are excellent substrates for SN2. So first thing you do is you have a substitution with the nitrile. But then what happens when you add the acid and the heat? The acid and the heat will hydrolyze the nitrile to a carboxylic acid. So if I draw this down here, nitrile gets hydrolyzed to a carboxylic acid. Okay. Okay, the next one here, cyanyl chloride. So you know what this does to a carboxylic acid. Makes the acid chloride. Make sure you got the 1, 2, 3, 4. 1, 2, 3, 4. And then with aluminum trichloride, in the presence of a acid chloride, you're going to get the acylium ion, which is great for Fritos Craft. So this is actually going to go here, and you're going to get ring closure. So the best way when you do an intramolecular ring closure is just count carbons. 1, 2, 3, 4, 5, 6. So that's going to be a 6-membered ring, and then you're just going to have a carbonyl there. So that's actually called a tetralone. Okay, the next one, 4-octine. Octine is 8 carbons. 1, 2, 3, 4. That means we have the YNE is a triple bond. These are linear. It's your carbon number 5, carbon number 6, 7, 8. And now you're adding potassium permanganate and water concentrated. So this is going to cleave the alkyne into 2 carboxylic acids. This is chapter 9. So 1, 2, 3, 4. You just draw 1, 2, 3, 4 carboxylic acid. And then you got 1, 2, 3, 4. So they're just going to make 2 of those. Okay, the next one, you got chromium. That's Jones reagent with a primary alcohol. So you know that oxidizes primary alcohols to carboxylic acids. And this will be an allylic carboxylic acid. So your product should look like this. You can draw that in there. Oh, this is an allylic group. OH. Okay, so the next one here, this is a new reagent here. It's borane. And boranes are really nice because boranes will reduce carboxylic acids to a primary alcohol. Okay, so it will reduce this carboxylic acid to a primary alcohol. So 1, 2, you have the phenyl group there, and then this is CH2OH. Okay, so you need to remember that. You will see that again. Okay, this is permanganate, hot concentrated, and it's not, this will not do anything to the aromatic ring. Okay, remember those aromatic rings are very stable, but this will do benzylic oxidation. So this is your benzylic position, and this is your benzylic position. And if you remember, it makes carboxylic acid. So you just oxidize both of those benzylic positions. And that's all you have to worry about, is the main product. Okay, the next reaction, so that's actually, we've done that as well. So the only new reaction here would be lithium aluminum hydride and the borane. These are your only new reactions. And they're the reduction of a carboxylic acid to a primary alcohol. Okay, here, this is esterification. We've done this. You have acid and an alcohol and a carboxylic acid. So now we're going to make the ester. So the ester would be here. This is the portion. It's 2-butanol. So let's draw what 2-butanol looks like. 1, 2, 3, 4. So it's this portion that's going to make the ester. There's your oxygen, came from here, and it's connected to your 2. So that is your ester. And then here's a cyclic ester. So this is esterification, but here's your alcohol portion, and this is your acid. So this is going to come here, and so this will actually leave as water, be your relieving group. So this will come up, and then it'll reclose. So now you got to count your carbons. 1, 2, 3, 4, and then you have a 5. So you have a 5-membered ring, and that it will be your ester right here. So this is your carbonyl right here. Take that blue, and then your ring, 1, 2, 3, 1, 2, 3, and then this is your oxygen from your alcohol that made this compound here. So this would be, and when it's a ring like that, that's actually called a lactone. When it's a cyclic ester ring. All right, the next set of reactions, how would you accomplish the following synthesis efficiently? You may use any necessary reagents. All right, so let's look at these. We have to draw the structures. Trans 1-bromo-2-butene. So there's 4, and there's trans, and there's 1-bromo, 2-butene, and you're trying to make trans 3-pentanoic acid. 1, 2, 3, 4, 5. Okay, so you have to look at what are you doing. You are, you'll want to turn this into a carboxylic acid here. So this could be your 5, 4, 3, 5, 4, 3, 2. So you need to add 1 carbon and a carboxylic acid. So you're adding 1 carbon plus a carboxylic acid. And so you can do this with a nitrile. So if you take this compound here and you react it with potassium cyanide, and then you hydrolyze this with H3O plus and heat, that will make a substitution reaction. Here's your 2, 3. And then this will get hydrolyzed to the carboxylic acid, which is equivalent to the product you want. Okay, the next one, 3-hexene. 1, 2, 3, 4, 5, 6. 1, 2, 3, 3-hexene. And you want to go to propanoic acid. 1, 2, 3. Okay, well, when we're shortening the ring, we need to think about oxidative cleavage. So if you cleave it there, then you and make carboxylic acid. So potassium permanganate and strong oxidizing agent, very concentrated, should cleave that alkene into the carboxylic acid. Okay, the next one, 2-butanol. 2-butanol. So that's an al. Okay, so that's an aldehyde. 1, 2, 3, 4. And you're trying to make 2-butanoic acid. So you just want to reduce the butene to butanoic acid. Oh, butenoic acid. Okay, so you just want to oxidize this up. So how do you oxidize an aldehyde to a carboxylic acid? You just add chromium. Cr2O7, H2Cr04, reduced terms. This is, or you could just write Jones reagent. Okay, any of those are going to give you the chromium species to do the oxidation from an aldehyde to a carboxylic acid. Okay, the next one you have hexanoic acid. So this is 6 carbons, 1, 2, 3, 4, 5, 6. There's hexanoic acid, and you're going to hexanol. So the Al is aldehyde, 1, 2, 3, 4, 5, 6. Count carbons. How do you reduce this down to the aldehyde? You're going to have to first make it an acid chloride, and then you're going to have to use dibal. This is important as this is a new reaction for you. So that makes the acid chloride, and acid chlorides can get reduced to the aldehyde using dibal, which is aluminum hydride, and it has 1 hydrogen, aluminum, and then diisobutyl. Actually, diisobutyl aluminum hydride is dibal. You could also use other stuff like lithium tri-tert-butyl aluminum hydride and stuff like this. But anyway, dibal, you can type in dibal, you can order that reagent, and you do this at cold temperatures, and it will reduce an acid chloride to an aldehyde. Now, the next one here, we're going from a carboxylic acid to an ester. This is esterification. It's called Fischer esterification, so you need the alcohol, CH3OH. The alcohol supplies the ester portion, and then you need a little bit of acid. Okay, this one you're going from a carboxylic acid to a primary alcohol. You know two ways in which to reduce that. You can do lithium aluminum hydride and quench it with acid, or you can use borane, which is the B2H6. Also, you can use borane as BH3THF. It's the same thing as B2H6, and borane will reduce that carboxylic acid. Okay, the next one here, we're going from a carboxylic acid to an amide. So to go from a carboxylic acid to amide, the best thing to do is to go through an acid chloride. So go SOCl2, which is thionyl chloride, and then react that with your amine. We've talked about this. This is acylation of amine in the last chapter 19. So there you go, methylamine, and with that thionyl chloride, that's called acylation of amine, and they makes amide. Okay, so that was chapter 19. And then we have this right here, and what you need to see is this is a dienophile, okay, because it's a, and you have a 6-membered ring. Okay, so when you think of that, you need to think of Diels-Alder. And so the Diels-Alder reaction would be with this right here. So let's line these up here. CO2, and see how it has the stereochemistry here? So it goes there, and then it goes there. And that gives you, let's bring it down here for our last one. That gives you a 6-membered ring that looks like this. You have a chlorine here, and you have a CO2H here, and then you can do, I wonder if that's a mistake, because I wouldn't actually do 2-step synthesis. So just go ahead and make this a chlorine and make that a double bond and just keep it there. Okay. Show how you would use extractions with a separatory funnel to separate a mixture of the following compounds. Okay, so we did this in class. We have benzoic acid. We have phenol. We have benzyl alcohol. You can make a better looking ring than that. Excuse me. Benzyl alcohol. And we have aniline. Okay. So, they're all going to be in your organic layer. Okay, so they're all in your organic layer. We'll make our organic layer is striped. Okay, then we add dilute HCl. Okay, so dilute HCl. This is in your water layer. And then what happens is things get protonated. So which ones are going to get protonated? Yes. The aniline will become NH4 plus Cl minus. And that goes into your water layer. Okay. So that goes into your water layer, and then you can wash that out. So now we have this gone. Okay. Then the next thing you want to do is, so the second thing you're going to do is you're going to add to your organic layer sodium bicarbonate. And that's a weak type base. And you're going to get deprotonation of only your carboxylic acid. Okay, so now this is going to go into the water layer because it's charged. So now you've washed that and your carboxylic acid's gone. So the only thing you have remaining in your organic layer are your benzyl alcohol and your phenol. Now the pKa value difference here, this is 10 and this is about a 16. So now you can add something like, so the third thing you want to do is add sodium hydroxide, and that will deprotonate your phenol, and now that will go into your water layer because it's a salt. And so now all you have left is your benzyl alcohol and your organic layer. All right, the next reaction is an esterification reaction, and you need to draw three-dimensional structures of the two stereoisomers formed. So CO2H plus CH3OH. Let's look. Okay, so we're doing the receipt. Oh. Okay, so this is S, lactic acid. So let's first of all, so this is your S. Two diastereomers formed. Okay. So what happens is here you have an acid and you have 2-butanol, and this is pure. So let's just draw this with this going back. Okay. And what happens is this carboxylic acid, this is going to stay. This is not touched. Okay. And it is this alcohol that is going to form your ester. This is your ester portion. And this is esterified by racemic 2-butanol. So what you have then is you have the S is not going to be bothered because the stereocenter is not touched during the reaction. Now, the carboxylic acid portion is this portion here from the 2-butanol. And if it's racemic, you're going to get one coming at you. And you're going to get an ester going back at that stereocenter because you're adding both R and S. So these are your two diastereomers, and they're diastereomers because, or there's two isomers formed because you have this is an S, this is an S, and then you have to figure out what this one is. So you look at this, you have 1, 2, 3. The hydrogen that you don't see is going back. So that's R. And then here you have 1, 2, 3, and the hydrogen's coming at you. So even though that would be S. Okay? So you have SR and you have SS. Those are diastereomers. if they were an enantiomer, it'd have to be SR and then RS. Both of these would have to change, okay? But because this S is still S and this is RS, these are diastereomers. So determine the relationship between the stereoisomers. Yes, they're diastereomers. Okay, show how you accomplish the following multi-step synthesis. You may use any additional reagents and solvents you may need. So this is problem number 11. I notice we can't really see the top. So let's just go ahead and rewrite that. We have a phenyl, CH2, CH2OH, and we're going to the carboxylic acid. Okay, so this carbon here is being oxidized to the carboxylic acid, and you can just do that by adding H2Cr4O7 Jones reagent. We'll oxidize a primary alcohol to a carboxylic acid. Okay, the next one over here is going from an alkene to a carboxylic acid. All right, so I put question mark on that. So this is definitely your this becomes your substitution of your carboxylic acid. I think that you could probably add HCN and then do the hydrolysis. So HCN would add the hydrogen in a Markovnikov proportion. Your nitrile would then add, because it's kind of acidic, so you protonate, and then your cyanide would come in, and you would get CH3CN, and then that would hydrolyze in acid and water to your carboxylic acid. And that's actually that problem. No, that's this problem. Okay, what about this problem here? See, you're adding a carbon. Yeah, so you're adding a carbon in the anti-Markovnikov. So, and you have an alkene. So, the way I would do that is I would do this Si2 borane, and then you oxidize that with hydrogen peroxide and some base. That's going to give you the anti-Markovnikov alcohol. And then you can react that with SOCl2, thionyl chloride. We'll make that, or you could tosylate it, tosyl chloride and pyridine to make that OH a good leaving group. And then you can add the nitrile then, so potassium nitrile. And then the third thing is H3O plus and water, warm that, and that will hydrolyze your nitrile to a carboxylic acid, and it would add one more carbon to the chain. Okay, the next one, I guess you could have done here, you could have made the alcohol using mercury sulfate, sulfuric acid, and sodium borohydride, and then done the same thing there. Okay, our next one here, we're exchanging the bromide for a carboxylic acid. This would probably be a nucleophilic aromatic substitution because you're exchanging a bromine for a carboxylic acid. And so we'll skip this one. Okay, the next one here is an acetal formation. So to do an acetal, you need either a ketone. You could use, well, actually, you want to add this first, okay? So to add this, you need to add one group. So first thing I would do is I would convert that to an acid chloride using thionyl chloride. And then you want to use a cuprate. So this is a Gilliam reagent. So it's always R2. Cu, R2 lithium. It's the Gilman. And it will stop at the ketone. So that makes it different. It only does one addition. So this will add to an acid chloride. This goes up and then it comes back down and the chloride will leave. So now you have a ketone. And then that is an acetal. So that would be made like this, and acid. You got 1, 2, 3, 1, 2, 3, and that would give you your product. Okay, this reaction here is esterification because you made an ester from an acid, and you have 2 of those. So I'm not sure exactly why. I guess you could reduce one down, but basically I would just go with, if this is your ester portion, which it is, you just need, what's a 5-membered ring? You just need the alcohol. So just go with the alcohol and then acid. And you add that and you'll make your ester. Okay, the next reaction, number 12, predict the major products formed when benzoyl chloride reacts with the following reagents. So what is benzoyl chloride? This is benzoyl chloride. With ethanol, you make an ester. So you're going to form the ester from ethanol. Sodium acetate. The sodium acetate looks like this. And it is going to form, let me show you what that looks like. So when you react this with benzoyl chloride, and make sure you can draw the intermediate that forms. So this goes here, and then forms a tetrahedral intermediate, O minus, there's your chlorine. Now you have and then what happens is this is a great leaving group. So this is going to come back down and this is going to leave. And now you have this is an acid anhydride. You have a new functional group. It's a derivative. Carbonyl, oxygen, carbonyl. The acid anhydride. Okay, the next one, aniline. Well, you all talked about primary amines with acid chlorides. That's an acylation of amine. So that's going to be an amide. Okay, so that's going to be amide. Anisole. Anisole, you might not know that structure. You might have to look it up, but it's OCH3. And now you got aluminum trichloride. Okay, and you got an acid chloride. So this is a Friedel-Crafts acylation reaction. So you're going to make your acylium ion or electrophile, and then you've got to recognize that this is an electron donating group. So it's going to activate, it's going to be at the pair position. So then your product is going to be OCH3, and then you're going to form a bond here with this compound here. And that will be your product. Excess phenyl magnesium bromide. So excess phenyl magnesium bromide. So this is phenyl magnesium bromide. Okay, and dilute acid. So this is going to do 1 with the leaving group. So you're going to form your ketone. And remember, ketone's going to add again because it's a Grignard. It's not like your Gilliam reagent. And you're going to make your alcohol. So this will be a triphenyl methanol. And you've actually done that reaction in lab. Okay, and the next one, the last one, is tributoxy aluminum hydride with an acid chloride. And that's like dibal, right? So when you take an acid chloride with dibal or some other mild reducing aluminum reagent, like dibal or this tributoxy, you're going to get the aldehyde. So this makes benzaldehyde. Okay, so then the last one, number 13, acid catalyzed transesterification, that means you're changing ester, and Fischer esterification take place by nearly identical mechanism. Transesterification can also take place by base catalyzed mechanism, but attempts at base catalyzed Fischer esterification are doomed to fail. Okay, so let's just do an example. This would be a good SAM question. So this is an ester. This is a methyl ester. And if you want to do transesterification, you can do this in base with ethanol. And that's going to give you, let's make this blue, instead of a methyl ester, now you're going to have an ethyl ester. You can also do this in acid and get the same thing. But it says base catalyzed Fischer esterification seem doomed for failure. Okay, so if you want to do an acid, well, when you do a Fischer esterification, this has to be an acid, carboxylic acid. So if you do acid here with ethanol, that works well, okay? So you get your ester. But if you try to do it in base, you get no reaction. And the reason why acid or base works well here is because when you're doing esterification, this can come in, okay? And this comes in and forms this tetrahedral intermediate. And then because there's so much, your solvent is ethanol, this will end up eventually leaving. This will be your leaving group. Okay? So this will be your leaving group. So the methoxy can leave. This is a decent leaving group. Now here, and here you have the acid catalyzed. But when you have a carboxylic acid, the intermediate, so we're looking at the intermediate here, with your CH2, CH3, in order to make your ester, this is a poor leaving group. And you got an O minus. So it's not going to leave. So the base doesn't work. But if it's acid, what happens? This would actually be protonated. This is protonated like this. And then you have your ethanol. So this is your intermediate. This is a good leaving group. So when this comes down and this leaves, you get your ester. But in base here, this OH is a poor leaving group. It's not going to leave. And that's why it does not work. Okay, predict the products of the following reaction. Phenol to acetic anhydride. Okay, phenol plus acetic anhydride. Okay, this is important. So here you have phenol and acetic anhydride. Be able to draw acetic anhydride. Okay. What happens is the phenol comes here. You actually form the tetrahedral intermediate. O minus CH3, O carbonyl CH3. This is a great leaving group. Okay. So when this comes back down, this leaves. And then what you get is CH3 carbonyl. You get an ester. Okay, so the phenol is your alcohol portion, acetic anhydride. This comes from your acetic anhydride. This comes from your phenol, and you get an ester. Okay, phenol and acidic formic anhydride. Okay, so acetic formic anhydride, there's your acetic group, and then this is your formic anhydride. Okay, and then that's what makes the anhydride. And so this time if you have phenol, you got to decide which one's going to be the better leaving group. So this is going to come and attack one of these carbons. And I'm thinking this is going to be your leaving group. And you're going to form an ester once again. And there will be the acetate. Okay, now we have aniline. And phthalic anhydride. So phthalic anhydride, you're kind of getting familiar with this phthalic structure. That's phthalic anhydride. And you have an aniline. So this is going to attack, and then this is going to open up, and then it's going to do it again. So it's going to do it 2 times. You're going to lose water 2 times, and you're going to make a structure that looks like this. Okay, and you probably recognize that you can react this with hydrazine and heat, and that would be like the Gabriel synthesis. That would release a primary amine, aniline, but that wouldn't do you any good because you're already starting with aniline. So why would you want to do that? Okay, the next one is anisole. So we've seen anisole before in the previous questions. So let's draw that structure. And succinic anhydride aluminum trichloride. So succinic anhydride is 4 carbons. You'd have to look this up probably. But that's succinic anhydride and aluminum trichloride. So what's happening here is it will make the acid chloride, and then it will add first here, and then you're going to get ring closure. So CH3, it would add here. So this, add here, through a Friedel's craft. 1, 2, 3, 4. 1, 2, 3. There's 4, and it's going to do a ring closure. Okay. That's kind of like an intramolecular Friedel's craft acylation. That's harder than anything I'm going to ask. Okay, here we have one equivalent of acidic anhydride with this compound here. So let's look at it. We have phenol, CHOH, and then CH2, NH2. So this is an ethanol. It's called an ethanolamine. Okay, we got 2 carbons here. And you're reacting it with acidic anhydride. Now, the reason why this is important is because you're going to acylate, meaning you're going to add this acyl group onto either the nitrogen or the oxygen, because these are your nucleophiles. So which one's a better nucleophile? You have to know these things, because this is last chapter, or this is organic 1. Is OH a better nucleophile, or is NH2 a better nucleophile? Okay, oxygen is more electronegative than nitrogen. So, more electronegative, it's going to be less nucleophilic. So, NH2 is better nucleophile than OH, which is better than fluorine. You know fluorine is a poor nucleophile because it is so electronegative. So the nitrogen lone pairs are going to attack this carbonyl, and then this will be a leading group. So this whole thing, this whole anhydride is your leading group, and your product then will be phenyl, CHOH, CH2, NH, and then you add the acyl portion. Okay, the next one's excess and acidic anhydride. Yes, you would get both of them. So go ahead and write, you couldn't discern between one or the other, and you would acylate both the nitrogen and the oxygen. Okay, so in this problem we want to do a synthesis. So we need to look at our functional group transformation. The first one, we're going from a primary amine to an amide. So this is an acylation of an amine. And so basically you just want to add this anhydride, this formal anhydride, and that would react. This would, with the amine, this would be your leading group, and you would make the amide. Okay, the next one here, you're going from a carboxylic acid to an acid anhydride. This is an acid anhydride. So the first thing you do is just react acid chloride with thionyl chloride. And then you can react that with just maybe sodium acetate, and that would make your anhydride portion. This would end up being your leaving group, and you would add this group here. Okay, here with the diol, you just want to add, this is called oxalic chloride, and so that would attack the carbonyl there. This would leave, and you would do it a second time. That's oxalic chloride. And you can look that structure up. Okay, so here we have one equivalent of this ester here, which, so you can, this is an isopropyl ester. And so basically I would just add H3O plus and one equivalent of the isopropyl alcohol. Okay, the next example would be an aldehyde, and this is a primary alcohol, and you want to make an ester. So I would protect the alcohol first by putting a large amount of this acid, and might not be an ideal synthesis. So what would happen here is that would protect this alcohol. Actually, you know what, let me do what I would really do. And you all don't have to know this, but you could add like some pyridine and silyl ether. So this is just a silyl chloride, and this would give you an SN2 reaction, CH2O silyl group, and this would protect that alcohol. And then you can oxidize this using H2Cr4O7 Jones reagent. So now you have a carboxylic acid. One, two, three, four. And CH2OH. This would come off in the acid. So, and then you could add a little bit more acid and heat if you need stronger acid, and you would get esterification, which would give you your product. This one here, you already have a carboxylic acid, so all you need to do is reduce the aldehyde to a primary alcohol, and you can do that just using, you wouldn't want to use lithium aluminum hydride. You could just use sodium borohydride, and sodium borohydride would make that a alcohol, and then you can add H3O plus and acid, and that will make your ester. Here we have methyl ester, and it's kind of funky because this is your carbon here and you have to increase it by a carbon. So what I would do is I would add BH3 times THF, or you might see this as B2H6, and the borane will reduce the esters but not the ketone. So you get that as primary. These would all be primary, CH2OH, CH2OH, and now you can react this with excess acid anhydride, acetic acid anhydride, excess, and that would acetylate each one of these alcohols. Okay, this reaction right here, I would add mercury sulfate, sulfuric acid, and sodium borohydride, and that will make the alcohol. The regiochemistry won't really matter here because it's substituted the same way on both sides. And then I would oxidize this. Let's come down here. So you have an OH. Now you can oxidize this using PCC, and that's going to give you your ketone. And what you don't know yet is that you can react this with lithium, or not lithium, actually LDA. LDA. It's a strong base, and it will depronate the alpha proton. And then you can react that with potassium nitrile. No, that's not going to work. How would you put that carboxylic acid there? You probably have to react it with some kind of magnesium Grignard formate. So don't worry about that reaction. Don't worry about that one. Okay, this one, proposed mechanisms for the following reactions. This is kind of important because you need to be able to write your tetrahedral intermediate. So here you have an alcohol. As long as you can just find your nucleophile and recognize that this is going to form a tetrahedral intermediate. And then CH, CH3, CH3. And then this is going to come down. And this is going to leave. This is your leaving group. And then you get your product with a deprotonation step. Okay, this one here, sodium hydroxide comes in here, does the same thing. So make your tetrahedral intermediate. OCH3, this is OH, and then that's your tetrahedral intermediate. This is going to come down here, and this is your leaving group to give you, and it would in base, so then it would deprotonate. So do this and then deprotonate. So first thing, add nucleophile addition to the carbonyl. Number 2, form your tetrahedral intermediate. Number 3, reform your carbonyl with leaving group, leaving. And then number 4, deprotonation step. Okay, here, this is acid, so you're going to get protonation. It's always the first thing. When you have acid, if you have a carbonyl, it activates that carbonyl. And then you have your nucleophile, which is water. And so now it's going to come in and form your tetrahedral intermediate, OH2. And then you see that this is going to be your leaving group. So these electrons will come here. This will be your leaving group. And then you get deprotonation step to form your products. Okay, this is a base. And so you have, and this is going to come in and do, this is an ester. This is a strong base. So the ethoxide is going to come in here and form your tetrahedral intermediate. So let's go ahead and draw the tetrahedral intermediate with O ethyl group here. That's your tetrahedral intermediate. And then these electrons are going to go here, and this is going to be your leaving group. It's kind of like an intramolecular leaving group. And then you form 1, 2, 3, 4, 5. So there's your 5-membered ring. And then on this carbon here, you have this carbon, and it forms O-ethyl, and then this one is your OH. And they're going to be on the same side because they're on the same side of this ring. So you could go ahead and draw your stereochemistry in. Okay, the next intermediate here is acetic anhydride and your alcohol. So your alcohol, go ahead and draw your acetic anhydride out. This is going to add, the nucleophile is going to add there. It's going to form your tetrahedral intermediate. CH3. Let me redraw that. All right. OH goes there. O minus. Then you have CH3. You have this portion, O, carbonyl CH3. This is your leaving group. So when this reforms, this leaves to give you your product. Okay, the next one is, this is an N-amine. You see the EN, the double bond, and it's an amine. And you have acid and aldehyde and an amine. So what's going to happen is you're going to lose water. Okay, so this mechanism was a mechanism you just took an exam over. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And the amine will attack the protonated carbonyl. You get a ring, 1, 2, 3, 4, 5, 6. You can draw that. There's your nitrogen. There's your OH. Now you have NH2. This is a protonated, and you're going to lose water. So this is going to be your leaving group, and here's this, so you lose that in there, and it forms this compound here, the unamine. Okay, here it's going to form an amide. So looking at that, we have an ester. The difference is here we have a leaving group. Okay, so once again this gets protonated, and then this is going to form the tetrahedral intermediate. OH here, and then we have, make this one blue, OCH3, and it's going to have that. Now what happens is when this comes here, actually what happens is this is going to be your leaving group because you have an ester. These electrons are going to reform here, and those are going to leave. So you're going to lose CH3OH methanol, and you're going to reform the carbonyl, and that's what makes the amide. Okay, the next problem, predict the products of the following reactions. This is your last page of problems. And the first one is going to be an ester. So you don't have to do your mechanism here, but basically it's going to attack there. Acid chlorides, that's a good leaving group. So your product, then you can just draw in your ester. The ester comes, the Fischer esterification comes from the alcohol portion. Okay, the next reaction here, you have an amine and an ester. The ester is going to be your leaving group. So you're going to make an amide. NHCH3. Okay, so you're going to make an amide. You're going to make an ester. Here, this is acylation of amine. So once again, this is going to be your leaving group. And this is going to be your nucleophile. There you go. There's your amide. It's going to make an amide. This one is an acid anhydride. So this is going to come in and open up, and this is going to be your leaving group. What's going to be interesting about that one, though, is that it's still attached. So this is still attached. So if you protonate this, this could actually leave, and this could also leave. And what's going to happen then is you're going to get an imide. So that's your nitrogen in between two carbonyls. And that'll make an imide, I-M-I-D-E. Okay, lithium aluminum hydride will reduce your ester to the primary alcohol. So that would just be CH2OH. It will reduce the amide to an amine. So there's your amine. This here, this is base, and this is a methanol. So this is trans esterification. This is an ester, an internal ester, and we're going to replace this ester group here with this methyl ester. So you want to count how many carbons. 1, 2, 3, 4, 5, 6. So you're going to get 1, 2, 3, 4, 5, 6, and that will just be an OH. That's going to open up and do a transesterification. You're changing one ester for another one. This one here is an ester with a Grignard. It's an important reaction that you've already learned. So let's look at that. This is going to be your leaving group. And so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then this phenyl magnesium bromide is going to come in here. And then we're going to, that's a ketone now, because remember, with Grignards, you're going to get 2 additions to make a tertiary alcohol. Okay, the next one here, we have a nitrile group and we have a Grignard. So remember the Grignards, then we'll do a nucleophilic addition and then we will hydrolyze that. So at this carbon, you're going to add your Grignard, and then this makes your amine. But then you're adding acid to hydrolyze that, and an amine will hydrolyze to a ketone. So your product then will be a ketone. We learned that in the previous chapter. Okay, so here we have an amide. We have a base. And base will hydrolyze amides to the carboxylic acids. So it will eventually leave, and so this is going to open up. Let's count how many carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And this will be OH. It's in base, so it'll be O, sodium hydroxide. And this one's kind of tricky because the NH2 will stay on the chain. Okay, so the next one we have here is, you know, I'm not actually, I think we're doing this one, and you can skip this one. This is really next chapter. And then this compound here is, would be like a transesterification. So once again, open up the ring here. This is your leaving group. 1, 2, 3, 4. So 5. 1, 2, 3, 4, 5. Make sure OH, and then you get O, CH2, OH, and I think we'll just stop there. Let's see. Okay, the next problem, predict the products of saponification of the following esters. You need to be able to do this, okay? So you need to be able to see that this comes from your alcohol. So then the rest of the portion would be, that's your formic acid, and your alcohol would be the phenol. Okay, here, this is your alcohol, and so this would be your carboxylic acid. Here, this is internal. Go ahead and draw your ring. This is your OH. You have 1, 2, 3. 1, 2, 3. That's your acid. Here, this is your alcohol. And this would be your acid. Okay, this one says, 2 widely used pain relievers are aspirin and acetaminophen. Show how you would synthesize these drugs. Okay, so this is a good little exercise. And you might come up with something different, and you might decide you don't want to try this at all, and that's okay. But I'm just going to show you how I think I would do it. Magnesium bromide, carboxylic carbon dioxide, and the second thing, actually let's just skip this for the time being. You guys have plenty to do. Let's just not do. Okay, then we're going to do number 20. Show how you would accomplish the following synthesis. Some of these conversions may require more than one step. Okay, so this is just good basic chemistry. Isopentyl alcohol. So isopentyl alcohol is 1, 2, 3, 4, 5. There's isopentyl alcohol, and you want to make isopentyl acetate. So this is CH3, and then this is your 1, 2, 3, 4, 5. So basically you just take this acid, acetic acid, with your isopentyl alcohol and add H3O plus and some heat, and you're going to make that ester. Okay, here we have, that's the Fischer indole, or the Fischer, this is the Fischer esterification reaction. Okay, pentanoic acid, so that's 5. 1, 2, 3, 4, 5. That's pentanoic acid, and 3-ethyl. 1, 2, 3. That's 3-ethyl, and you want to make the nitrile. So pentane nitrile. 1, 2, 3, 4, 5. And so to do that, I would add thionyl chloride, and then I would add ammonia, and then I would add a dehydrating agent. So that's a new reaction, POCl2 or P2O5. So read about that. That will dehydrate a amide to a nitrile. When I say dehydrate it, you're going to lose water. Okay, the next one, isobutylamine. So make sure there's 4. 1, 2, 3, 4. That's isobutylamine. And you want to go to isobutyl in isobutyl-formamide. So basically this is the acylation of an amine. You can do this with acid anhydride if you want. Probably be the best. And this would be your leading group. And that's how you could make that compound. Ethyl acetate. So what does ethyl acetate look like? Well, there's your ethyl portion, and there's your acetate. And you want to make 3-methyl-2-pentanol. So let's draw out 5 carbons. 1, 2, 3, 4, 5. 3-methyl. There's your 3-methyl. And 3-pentanol. Okay, so the best way to do this would be okay, I'm not real sure on this one, so we'll just go ahead and skip that one. Go on to the next one, cyclohexylamine. And you want to go to N-cyclohexylacetamide. So there's your acetamide group. And basically this is just, you could react that with an acid anhydride. Should be nice and mild. And this would be your leading group, and that should work. Bromocyclohexane, and you want to make dicyclohexylmethanol. That's a secondary alcohol. So you should be able to just react this with an aldehyde. So you can react that with cyclohexylaldehyde, add magnesium and ether to make the Grignard, and then quench that after you add the aldehyde with some acid to make a secondary alcohol. Because Grignards will react with aldehydes to make secondary alcohols. This one here, dimethyl oxalate. So your oxalate looks like this. So this would be dimethyl with 2 carbonyls, and you react that with your amine, and let's see, I don't think, maybe I stopped working on them at this point. So let's just see, this you would want dimethyl oxalate. I think that's not dimethyl. Skip that one as well. Okay. Okay, and this one here, you just want to convert the primary alcohol to a nitrile. So the best thing to do is to just react that with vinyl chloride, and then you can react that with NH3. So that will give you your nitrogen that you need. So you got CH2, NH2, and then you want to dehydrate that. So you can take amines to the carbonyl by just reacting with POCl3. It's a dehydrating reagent, and that should make your nitrile.